Okay, guys. Today we're going to talk about chemical periodicity. Last class we talked about how to draw Bohr models, and we talked about the fact that the electrons on the outside of the Bohr model were a way for us to talk about how they would react with other things and to understand what they behaved like. Today we're going to talk about how the periodic table can be used to predict some of those properties that again relate back to those valence electrons. But before we get started, we're going to talk about who invented the periodic table, and that would be Dmitri Mendeleev. He was looking for patterns in the physical and chemical properties of the elements, so he basically had these cards that he had written down all of the things they knew about each element, the atomic charge, or the atomic number, which is the nuclear charge, the mass of each one, the reactions it went through, that sort of thing, and he was arranging and rearranging that table. And in the end, he was able to come up with a table, even though he only had about somewhere between 60 and 70 of the elements that we now have on the periodic table of the 118. But what made Mendeleev sort of stand out from the rest of the people that were trying similar things at the time was the fact that he was able to predict the existence of elements that we didn't know about before. So when he had a spot in the table that didn't quite work out, he would predict that there was an element there. And turns out he was pretty good at it. He was able to predict some elements that nobody had discovered yet, and then when people discovered them, it turned out his data about those elements was really spot on. And so it made it easier to discover elements, and it proved that his model for how this thing should be set up was correct. His table, one of the things that organized his table was the atomic mass, or the average atomic mass of the elements. It turns out, though, that you get a little bit better table, and the one significant change we've made since his time was when Henry Moseley said that we should use the nuclear charge, or the atomic number, instead of the mass for the elements. Now, it didn't change a lot, but there's a couple spots, like where nickel and cobalt are on the periodic table, that whole thing flips. So, again, just switched around a couple of elements, but it is the one we go with now. So when you start at the top left-hand corner of the table and you read like you would in a book, right, left to right, top to bottom, you end up with a set of elements that, or you end up with adding 1 to the atomic number each time when you go through each element. When we organize the periodic table, we have periods, which are the horizontal rows going across the table. So if you look at lithium on your periodic table and go across to neon, that would be a period, so moving left to right. And then groups or families tend to be the vertical columns on the table. So lithium and sodium, potassium, rubidium, cesium, francium, those are all in the same group or family. In that case, the alkali metals. The periodic law tells us that when the elements are arranged in order of increasing atomic number, there's a periodic pattern to their physical and chemical properties. So the properties of the elements repeat themselves if they're set up in the way that they are on the periodic table. And we tried to set up the periodic table so that when you got back to the left-hand side, those properties started repeating themselves from there. Atomic radius is simply a way for us to decide whether or not, or decide how big the atom is. So if you picture these yellow dots as being like the nuclei of two atoms that are next to each other, so two oxygen atoms, for example, we measure from the center of one nucleus to the center of the other nucleus, and then half of that distance, which would be the radius, is attributed to that particular atom. So the stuff on the left, or the left side of that line, is for the atom on the left, the right side of the line is for the atom on the right. And that allowed us to get a sense of how big the atom is. Now when we look at the periodic table, we find out two trends. One is that when you go into a group, so going down a column, the atomic size increases as you move down a group. This makes sense because the atom is going to gain a shell of electrons, like we talked about last class, each time you move down a row. And so that extra ring means that the inside rings are shielding the outside electrons and allowing them to be farther from the nucleus. But the counterintuitive thing is the periodic trend. So as you move from left to right, then the atomic size goes down, which seems weird because you're adding electrons, but you're also adding protons. And since those electrons are going into the same ring as you move across a row, but the protons are pulling more toward the center, those electrons actually shrink in toward the middle, and so you end up making a smaller atom as you move to the right. So if you wanted to make the largest atom, you look for francium, which is down at the bottom of the table all the way on the left. And if you want to make the largest atom, you'd go into the upper right-hand corner and find helium. If you have a positive ion or a cation, it's going to be smaller than the atom it was formed from, and a negative ion or anion is going to be larger than the one it was formed from. So if we pull an electron out, the atom shrinks. If we push an electron in, the atom gets bigger. And then last but not least is electronegativity. So this is the tendency of the atom to attract electrons to it when it's chemically combined with another element. So when two atoms bond to each other, the electrons in that bond, if one atom is really electronegative and the other one's not, the electrons will move toward the electronegative one. And this electronegativity decreases from top to bottom and increases from left to right. It's important to remember the noble gases are not included in this because they don't form bonds, so we don't have any way of measuring their electronegativity. So when we say it decreases from top to bottom and increases from left to right, we're saying that the least electronegative atom on the periodic table would be francium. Again, that was the biggest atom. It's also the least electronegative. And then the most electronegative atom is not helium, because helium is a noble gas, so we get as close as we can to it, which would be fluorine. And those are the trends we need to know. There's also an assignment for you on Google Classroom about picking an element and designing an infographic for it. It's just an image that depicts a bunch of information for that element. Hope that helps.